Hello, everyone, and welcome to GP Tuesdays Workshop Edition. We're very excited. Yeah, thank you. We're very excited to be teaching here at Miami-Dade College and also with GP Tuesdays. So we are right now going to be teaching you about computer vision from classification to generation. It's a very exciting field. We wanted to show that, AI is more than only LLMs. Although LLMs are extremely important, computer vision is also extremely important, which Aleksei will be teaching and showing everyone here today about how important and exciting it is for the industry. GP Tuesdays now has been around since June of 2023. We've been doing now this every single week, providing AI education from multiple agents to great speakers from Google, Meta, Amazon, Microsoft, and many other companies. We've had Crew AI, we've had many other great speakers here, but now we also want to be able to teach you how to use AI in your day-to-day life. We want to be able to upskill and reskill folks because AI education is very important, and the way of the future is going to be by using AI from a lot of different ways, through AI tools to different programming techniques, et cetera. So we want to be at the forefront and being able to teach you all these different skill sets. We want to help people get jobs, whether you're a junior developer or a senior developer. We want to be able to help you get into the AI field. And so without further ado, I want to bring on Aleksei to talk more about computer vision. And I guess a little bit before that, Aleksei has been a really important member of our community, a good friend of mine. So I want to thank you, Aleksei, for helping out GP Tuesday so much.
Thanks.
Yes.
I'm very happy to present here. Thanks, guys, for coming. Quick introduction, what is computer vision and why we decided to have workshops in this field. For the one who is new in AI field, you maybe heard a lot about LLMs, about ChatGPT, and this tools is actually machine learning model or neural networks. And the field of machine learning is much broader than just LLMs. It has different fields. For example, computer vision is one of the biggest, and it has a huge demand in the business. Most of the companies using computer vision in a day-to-day basis in different tasks. For example, video analysis, video analytics, also image classification, or maybe you also saw amazing pictures that being generated using AI, for example, Midjourney, DALL-E, or Stable Diffusions. But before we go there, we should understand the basics, how simple models can be created. Just in 1 hour, we can create a couple of models. And when you learn that, you can start looking for more advanced models. You can really understand very deep how it works. And this workshop will be about computer vision. These are largest domain in machine learning. Predictive analytics is, I think, the biggest one. Predictive analytics, when you have to predict, let's say, demand of the products, or you have to predict the price, stock market, and when you have to predict some variable based on others. Recommendation system is also a big field that you see in Instagram when you scroll videos in TikTok or in music applications like Apple Music, when it will recommend you the music to listen. Reinforcement learning, it's a very advanced technology that is being used in self-driving cars, in robotics, in game theory. It's also used. It's, I think, a very promising technology that will be adopted across different industries. and it's very advanced. Natural language processing, it's a broad term for, we already covered this in GPT Tuesdays. You can watch previous lecture we had. For example, LLMs, ChatGPT, it's all about natural language processing. And in natural language processing, there are much more tasks, not only language generation, but also classification, translation, sentiment classification, many more. And the topic that we will cover today is computer vision. Let's talk about tasks, common tasks in computer vision. I would say the simplest tasks in computer vision is classification. If it's simple, it doesn't mean that it's not useful. Most of the business use cases being solved by this task. For example, we have 3 types of classification. Binary classification we have when we need to predict 2 classes. Let's say we have to train the model to predict is it the cat on the picture or dog. We have only 2 classes. That's why it's called binary classification. If we have more than 2 classes, it's a slightly different task and a different model architecture. It's called multi-class classification. There will be a small difference in the architecture. In the last layer of neural network, we will have not 2 neurons, we will have n neurons. And on top of that, we will be using different activation function. We will be using softmax instead of sigmoid activation function. And the loss function will be also different. We will be using cross entropy. For binary classification, we use binary cross entropy. And for multi-class classification, we use cross entropy. And we have also multi-label classification. Multi-label classification is similar to multi-class, but the only difference here, we can predict multiple objects in the multiple classes for one image. For one input, we can have multiple true classes. And in the architecture, we will also have a different activation function. We will have sigmoid on top of our neural network. We will have n neurons in the last layer and the sigmoid activation function. And the loss function will be binary cross entropy. Here are the most popular neural network architectures that can be used for classification. For example, very first neural networks like AlexNet, VGG, Inception. These neural networks basically established our AI revolution that we can see now. Starting from these models, the industry started being developed. Also, we have a couple more advanced models like ResNet and EfficientNet and visual transformers. These are current state-of-the-art models that has more complicated architecture, and they have higher accuracy, and they're bigger. It's harder to train them. And visual transformer is based on well-known transformer architecture that being used for large language models. And the only difference will be inputs here. How there is difference how we preprocess tokens for a language and how we preprocess image. To pass image to the transformer, we have to split image to the patches, and each patch, it will be a small cell in the input image that can be represented as a token. And there are 2 basic operations in computer vision. Let me hide it. First one is called convolution. You can see in the bottom. And the second one is called pooling. It's a very simple operations. Let's look into convolution first. On the left, you see the matrix. This is how we represent image in computer vision. If we have not colorized image, we will have just one matrix. But if we have colorized image, we will have 3 channels. One channel for air color, then another channel for green color, and the third one for blue color. And convolution, for convolution, we can consider it like a function that will transform input image into higher dimensional space, into hidden space. It's like a function of projection, where we have to make element-wise multiplication. You see dark blue color on the left, and you see orange color on the kernel. We make multiplication one by one, element-wise multiplication, and then we have to calculate sum across all these 9 multiplications, and we will get a value 53, for example, green color. This is just one operation of multiplication for input image and for kernel. And in computer vision, we have to slide this kernel through the image and run this multiplication multiple times. And we can change step, how we slide this kernel through the image. It's our hyperparameter. It can be just one step or multiple steps. But at the end, you will get a feature map where we have green color, 53 number. It's called feature map. And the kernel in convolutional neural network is called filter. And usually we have multiple filters, multiple kernels. And number of kernels defines depth of the hidden layer. Another basic operation called pooling. You can see it on the right. Pooling, it's a very simple operation where you have to split your input image into cells, like a grid. And in each cell, you have to find a value, for example, maximum or average. For maximum pooling, we just, for example, for maximum pooling, we just find the maximum between these 4 numbers, and it will be 9. For blue color, it will be 2. And we will get just matrix of smaller dimension. Using pooling, we can reduce dimensionality of our hidden layers, feature maps. And convolutional neural network is basically combination of convolution layers and pooling layers and activation function. We can use like a lot of convolution layers, like dozens of even hundreds of layers, and we can combine them together, experiment differently, and more layers we will have, more complicated neural network we will get. And at the output of this model, we usually have a flattened layer where we just stack numbers of the final feature map together in one-dimensional vector. And at the end, we will have a fully connected layer, dense layer, and softmax activation function for multi-label classification. that will predict probability of the classes. Do you have any question? Is it clear, or do I need to explain something here?
Well, I'm understanding it. So this is the process where I guess you're taking the images and I guess you call it arrays where you process the information. So when you say flat, you mean it's where it's that end output where I guess you're finishing up at that end process, I guess. Is that what you mean by flat?
Flatten layer is here. So when we apply convolution and pooling operators together, we get these feature maps. We have, for example, if you have 3 kernels, you will get 3 feature maps. If you have 4 kernels, you will get, here if you have 5 kernels, you will get 5 feature maps. And here you get 8 feature maps. Here is how much, like 10. And then we just get numbers from all of them, stack them together into one array. And then this is a regular fully connected layer of the neural network that predicts final class. This is how image being represented and passed through convolutional neural network.
Can you repeat the question for Aleksey?
Sorry?
Can you repeat the question for Aleksey?
The question was, how do we, what is flattened layer, and how do we get numbers for flattened layer, right?
Correct. So the flattening takes place before you go through that, the array process.
Yes. Yeah. We need flattening to prepare data for fully connected layer. Because a fully connected layer expects two-dimensional input. One dimension is your input features, and second dimension is batch. In the batch, you have like multiple 64 images. That's why we have 2 dimensions. But here, for simplicity, we just consider one image. And in one image, we will have one-dimensional input.
Now, one image is not the whole thing, like pieces of the picture. You're kind of breaking it up into tokens and then processing it, I guess.
We're not breaking it. We multiply it with kernel.
Okay.
So after multiplication, we just multiply 0 with 0, 60 with -1, 113 with 0, and we will get 9 numbers, because we have 9 numbers here. And then we sum them, we calculate a sum, and we will get one value here. And when we move this kernel through our image, we get more output here.
So in this case, on our left, this is basically the values of pixels of the original image, right? So all we do is the kernel has the weights, right? The trainable weights, and then with those trainable weights, we just multiply the values of pixels of the original image, and then apply pooling on top of that, right?
Yes.
Okay.
Yes. So kernel, this comes from classic machine learning. Classic computer vision. Before neural networks, they explicitly defined numbers of the kernels. They had like hundreds of different predefined kernels by scientists. And they used it to get shapes of different objects. But when neural network developed, this weights being trained automatically now. So it's not predefined by scientists. Now neural network will be able to find better values here.
Is this through backpropagation?
Yes, yes. I think Mike is dead.
Is this the most modern process?
Sorry?
Is this the most modern process?
Yeah.
Is this the vision transformer process? for
No, this
computation?
is just a simple convolutional neural network. It's not a visual transformer.
Okay,
It's just a convolutional neural network.
okay, thank you.
Let's move on to another task. Object detection is also second most popular task in computer vision. In object detection, we have to find the bounding box which will detect the position of the object. For example, we can use object detection to detect faces in the photo or in the video, or we can use it to find any other objects, like any objects. Meta developed foundational object detection model that can detect any objects. For example, cars, houses, trees, dogs, and anything else.
Can people use that meta?
Sorry. Can people use that meta model that was released?
You have to carefully read the license they published. Probably not for commercial usage. Somehow for research and study, maybe. I'm not
Okay,
sure about their license.
that makes sense. Thank you.
We have two families of object detection models. One-stage detectors and two-stage detectors. Here you can see RCNN and YOLO I listed. These are very popular object detection architectures. The difference is that RCNN is a two-stage neural network. In the first stage, it predicts regions where it proposes to find objects. And in the second stage, it classifies those regions. It's very slow, but it's accurate. And YOLO, it's called You Only Look Once. It's a one-stage detector. It's super fast. It can be adapted for real-time video analytics. For example, you can see it in the video cameras when they detect faces or people. They most likely use YOLO architecture. How YOLO works? It splits the input image into grid, and for each cell in the grid, it predicts the position, how the model should refine anchor boxes. So here you can see anchor boxes. These boxes like initial positions of the bounding boxes. And through the learning process, for each grid cell, model predicts how it should refine it, where to move, center of the bounding box to find the object. And second loss is classification. In addition to position of bounding box, it classifies the object. And after it finds multiple bounding boxes, it uses an algorithm called non-maximum suppression to filter redundant bounding boxes. So it basically removes trash, and at the end you will see the only final predictions with output.
Trash meaning noise?
By trash, I mean bounding boxes. For example, before non-maximum suppression, you may see multiple bounding boxes covered dog, and there will be different shape, different scale, but all of them will be covering dog. And it will only keep one of them, which will have the best precision.
So when you say the small boxes are called noise, like is it the noise of the algorithm that's making those small boxes?
Yes. Yes, it's the design. In the design, they just scan your data set. They calculate the statistics of the objects, how big the objects, in the training data set. And they put anchor boxes. And anchor boxes is just a lot of different bounding boxes in the image that will be used for training. And through backpropagation, in each step, a model will predict where center of bounding box should be moved, to the left, to the right, and how width and height should be changed to get the best intersection over union with your object. One additional task is also very popular. For example, in self-driving cars, this task is crucial. It's called segmentation. In segmentation, model tries to predict for each pixel in the image, it will try to predict the class of the object. For example, in semantic segmentation, you can see that we have different colors for different types of the object. For a road, we have a purple color. For pedestrian, we have red color. For cars, we have blue color, and so on. For each pixel, we will have the class. Model will predict class, which will define the color. In instance segmentation, a model is trained to predict not all pixels, but only some specific objects. For example, for cars and for humans only. Everything else will be ignored by the model. And panoptic segmentation is a combination of semantic segmentation and instance segmentation. It will be able to distinguish different cars. For example, in semantic segmentation, we have all cars will have a blue color. And you cannot recognize where is which car. But in instance segmentation, each car has different color. And in panoptic segmentation, we can understand for each pixel which object it is, and we can differentiate different objects of the same class. And the most popular architecture here called UNet. It's called UNet because of the architecture shape, similar to U character. You can see in the layer 1 at the top, it predicts so in between layer 1 and layer 2, we increase depth and we decrease width and height using convolution and pooling operators. And when we go from layer 1 to layer 5, the depth being increased. And then when we go back, we decrease depth and increase width and height. And at the end, we will get same shape of the input image, but the ground truth will be a mask. Basically, those colorized images that you saw before, it was ground truth for the image labels, and model is being trained to predict those colors. And the final task we will cover today is generation. We have unconditional generation, where model will predict, will generate faces of the people that don't exist, for example. We have conditional generation, when we can prompt the image, we can explain what we want to see, like Midjourney and DALL-E, it's a conditional generation. And the model will try to generate image based on your prompt. And we have also image-to-image translation, when we have original image of any object, and we have a reference image. And the model will try to use a reference image style and mix it with original image. And you will see, for example, a very beautiful face masks here, beautiful style, and it's called image-to-image translation. The common architectures for generation is GAN-based models, generative adversarial networks, and diffusion models. Here you can see simple GAN architecture. In the model, we have real objects, a real training set, and we have additional model that predicts similar images. For example, let's say we have thousands of images of the numbers, human written numbers. And this generator model will try to generate image with human written numbers, but input will be a random noise. And we have additional neural network that will try to distinguish between real human-made images of the letters and artificially generated ones. And this model will predict real or fake. And this is, they will try to compete. A generator will try to hack discriminator, and discriminator plays a role of the officer that will try to distinguish which is real model, which is a real picture, and which is fake. And it will propagate loss to a generator. And they will play like a game theory, they will compete, and after thousands of iterations, generator will become better and better, trying to hack discriminator, and it will become absolutely incredible to where you cannot recognize the difference between real and fake images. This is how generative adversarial models works.
So you must discriminate in order to find out the truth, eventually?
Yeah, so this discriminator is a teacher for generator. Without discriminator, generator will not be able to learn how to generate very good pictures. It will always propagate loss function to generator, and generator will, it has to get better in order to win game. If it doesn't, then your model will not be able to learn. A discriminator is a teacher for a generator.
Is this process of the transformer architecture also at the moment where the generation receives?
Kind of. They have reinforcement learning with human feedback approach on top of foundational model. Well, where people basically they collect a lot of feedback from people, which response is better, and they train model to simulate human human labeling process. So they have a copy model that will simulate how people will evaluate model response, and they also propagate loss to the foundation model.
So do you think that like the jobs from data annotation, I don't know if you've heard of them, where we help train these models, is that possibly that reinforcement learning that's optimizing the foundation models right now? Those big frontier models, is that what could be happening?
Sorry, I didn't get the question.
So the discriminator for foundation models are actual human feedback, right? Reinforcement learning. So there's positions in the industry right now where you give that sort of, I think it's that role in order to better the foundation models. So they're using humans to give it more of a human touch, right? Like I guess an accurate sort of real life situation, instead of a discriminator.
Yeah, it plays similar role, but are you asking that can neural network replace this role, like human feedback, or what?
It seems like it could.
Yeah, yeah. If it happens, then we will get like exponential growth of the model, but I'm not sure. I doubt it will happen.
Or even like 2 layers above that.
I don't know. So it will happen, then model will be able to train himself, like infinitely.
So in this case, we have the training set, and then we have the generations of the fake images. So are you saying that the discriminator essentially, as you're training, as you're generating fake images, once the fake image can kind of pass the discriminator, then it succeeded the game?
Yes, discriminator, it's a supervised model
Right.
that they have also examples of real images and fake images, and that is being also trained in real time. And but it plays a role like a teacher for a generator.
Amazing. Thank you.
But it's very hard to train generative adversarial networks because it's not stable. You have to spend a lot of time spending on hyperparameters tuning and updating architecture. So like it's not really efficient. There is more advanced approach called a diffusion model. We will also look into it, and it's more stable.
What is the structure behind the generator? Is it a diffusion model or?
No, it's convolutional model.
Oh, CNN, right?
So it's yeah, it's CNN. It's half of UNet. So we looked
Okay.
into UNet. So you see here, we had a second half where we have an input tensor here, which is noise, and it will upscale image to the original shape. This is a generator.
So it's still a neural network, right, inside of it?
Yeah, it's neural network. Yes.
Thank you. For the GAN model the architecture you just spoke about, how computationally intensive is it to, and I'll probably ask this question for every type of model you're talking about, but how, given that it's always competing and generating, how intensive is that on, computationally, what kind of how high performance do you need for GPU, for example?
It's super expensive.
Okay.
Yeah.
Okay.
So GAN neural networks is one of the most expensive in terms of computational cost. You need to have latest GPUs. You need to have hundreds of thousands images. You will have to train it for days or weeks or months to get it really good. For example, you can read about style GAN model. They invested, I'm not sure, but a lot back then. Style GAN is very huge model. It has like its size of the model is 1.5 gigabyte. It's very big for computer vision model. This is another model for generation called stable diffusion. Stable diffusion is easier to train because of the nature. It doesn't have a generator and discriminator. It has two directions, forward diffusion process and denoising process. In the forward diffusion process, we have input image at the top, and we have encoder model. It's a neural network that will represent image in high dimensional space. And then it will step by step apply noise to to the input image, random noise. It will have like multiple steps where original feature map will be noised a lot. And then, let's say we have multiple steps here, T steps. Then we have another process called denoising, where a neural network will learn how to denoise the noise that we just added. But we also have a condition here. For example, the condition could be your text prompt, the condition could be the image, or anything else, or it could be mask. And using UNet, it will also try to remove the noise from the image to get the original picture. And this removal process is happening using visual transformer. Here you can see query key values that this feature map being split into multiple chunks. And each portion, each part of the feature map plays a role like a token for transformer. And here we have U-shape also, that will remove the noise from the image. Is it clear? Do you have maybe any questions? This is architecture. Training process, it's like on top of it. And this is just an architecture.
Aleksey, can you explain why it's better than the GAN?
It's hard to tell. Actually, it's a really theoretical question. Maybe, I think in theory, it's not better. In theory, it's the same. You will be able to achieve same result in ideal world. You will be able to achieve identical pictures to the real world. But it's all how it's engineered. It's very hard to engineer GAN network as good as stable diffusion. Stable diffusion is, yeah, so probably because a training process is harder when you have multiple networks playing against each other. You have to play a lot with architecture, with data, with deeper parameters, with computational costs, and it's just more expensive. And the diffusion model is it's a different paradigm where we have to add noise and remove noise. It's different. No, it's not game theory here, but it's efficient. Model will learn how to remove noise, and then you just pass random noise, and model will be able to generate something from random noise based on the condition. Today we will work on two tasks, classification and detection. First task will be to develop a computer vision model that will predict 4 classes or 4 input image. We have 4 different anomalies. The model will have to predict anomalies in the photo. Is it overexposed photo or blurry photo or no people in the photo or good picture with no anomaly? So we will have 4 classes. And these are examples of the first class with incorrect exposure. These are examples of blurry photos. These examples of just a nature where we have no human. And these are examples of good photos where we have people present and not blurry and not exposure photos. And I'm going to send a link to Jupyter Notebook. So you can go to Telegram channel, GPT Tuesday, and open link, and I'll show you what to do next. Are you able to open the link?
Great. So yeah, it's in the Telegram. So opening that up now. If anyone needs any help, please let us know.
So in this folder, it's called Workshop. You have to find Jupyter Notebook, multi-class classifier, and open it in Google Colab. Are you able to open it? So then you have to copy that, click File, and save copy in Drive. It will create a copy. Then you will open a new notebook. It will be a local copy in your Google Drive. Then you need to click Connect GPU. In my case, I don't have a limit. I will connect without GPU. And first we will prepare the data set. I have a links here to the data set. You don't actually, I think you will not be able to run it before you download data sets to your Google Drive. Let me check. Data set, 2 gigabytes. So if you want to run it yourself, you will probably have to copy data set to your Google Drive first, and then you will be able to run it in your local notebook. But now we will probably try to run it to my notebook. Sorry? Are we making a copy of the data set and running it now? Yeah, let's try to do that. Let me try to look what we have, because I have everything in my folder. It's downloaded? Yeah, now just create create folder in Google Drive.
In my personal.
Yeah.
Oh, sorry. You upload.
Name it somehow. No, you don't have it. And move the data set here. Organize. Move. Yeah. And you can also move.
That is installing locally. Was I supposed to do that?
Sorry?
I'm downloading it locally. Should I have not?
No, you don't need to do this.
Oh,
You
okay.
can cancel it.
Okay.
And OP multi-class classifier notebook. Open the notebook.
Oh, thank you.
And you will have to change the path. Scroll down. Not here. Scroll down. Here. instead of my, you will have to put your, instead of leaders of digital, put November 16th. Yeah. After we moved our data set to the folder, for example, what you can do is you can copy this data set to your folder in the Google Drive. Then we will copy. Do you have another mic? It's not working.
Or do we keep cutting out?
You sure it's on? It's not turning on.
Sometimes the light color is red.
Yeah, that's because you press the button. You have to be careful not to turn it off.
Oh, okay, okay.
Can we go over real quick how to get the data set into the folder?
Yeah, let me try to show you here.
Maybe we can do a step by step.
Yeah, let me try. I'll create another folder. The problem is I have everything in Russian. I'm not sure how I can change it.
Okay. Power of AI.
So create folder, then GPT. I'll call it GPT. Create. And now, if you open the workshop folder, you will have to I'm not sure if I have it in my menu because I have this in my folder, but in your case, you will have to move this into the folder that we just created, like GPT. Move there. Can we actually copy instead of move?
You should say dataset.zip, not copy it.
Yes. So we will create a copy. I'll create copy first, then I'll move it to GPT. And I will also create copy of the notebook and move it to the same folder. Save copy in the G drive. And I'm gonna try to move it also. Move GPT, select folder.
So in total, we moved dataset.zip and multi-classifier notebook.
Yes.
Just those two?
Yes, this is what I moved here. If we need something else, we will figure out and move it as well. Maybe minutes.
And do we have to remove the name? Yeah, dataset.zip, then copy out, do we move that to it?
It's not necessary.
Okay.
I just hate it.
Same here. Awesome.
So let's open copy, and now we will have to change name. So it will be GPT dataset. You keep content drive, my drive. You just replace Leaders of Digital Workshop 1 to your folder name, GPT in my case. And let me connect first. So, not such file or directory. So you can check what folders you have Oh, looks like it's not connected to G Drive. Runtime. Oh, if you want to connect to Google Drive, you have to click folder first in the notebook. It's called Files. Click here. Then you have to click Mount Drive. You have to connect your Google Drive to the notebook. Now Drive is available, you can see here. And now let's try to check. Yeah, it can get access to my Google Drive. And we will copy the data set from Google Drive to our workstation, local path. You can see that dataset.zip appeared here. It's taking time because dataset is quite big, it's 2 gigabytes. It took 42 seconds. Then we unzip this archive. So we got our folder, dataset, and this folder will have 4 subfolders with our 4 classes: bad exposition, bad quality, good quality photos, and non-person. We have 4 classes. Now we can load all of our dependencies. These are Python packages. For example, scikit-learn is being used to split our dataset into train tests. TensorFlow, Keras. Yeah, we will be using Keras for this example. I used to use Keras before for simple prototyping, but now I'm more into PyTorch. But for this example, we can try Keras. And yeah, we import our neural network model, sequential. We will import image data generator to prepare data for neural network. We import our layers that we will be using, dense layer and average pooling. We will be use accuracy metrics here. We will be using k-fold cross-validation to prevent overfitting. And we will be using hyperopt to optimize hyperparameters. And pandas numpy will be used for preprocessing. And pyplot will be used to display results. Is everybody able to run the code? No? Let me see. It's not mounted?
I don't think so. Sorry, this is my work's computer too.
Try to go to content. No, okay. So, content. Yeah, looks like it's not mounted.
Okay, I never didn't get that far. I guess I need to refresh. Thank you.
So, I haven't seen this part in my code. Did you edit this cell?
The cell?
Continue. Did you add this one or it was in my code, original
That
code?
was in your code.
Okay. Okay, why I don't see that mount? Grant, do you have issues?
Let me see real quick. Covering the wrong one. Let me see if I got it. So I presume just the files here, right?
Click here.
Yeah. Too many sessions.
Just close. No, you have to kill it, not just close.
Oh, really?
Yeah. Cancel.
So refresh helps.
Click runtime.
Yep.
Manage sessions.
Yep.
Oh, you have just one. Okay, close.
Close. Okay.
And click here. Why it's too many sessions?
Should I just close it or?
Let's try to terminate and let's try to recreate it.
Okay. So close it. Refresh.
Refresh. And connect.
Connecting. I moved some files around, so maybe that was an issue. Yeah. Put the two in here. Is that right?
What?
The data set.
Yeah, it's right. Let's see. No, it's still connecting. It's not connected.
Okay. Different time.
Yeah, you can see here.
Yeah.
How's going? Good.
It does need some changes to words. I got it working.
Okay. Cool. Looks like something happened.
Connected. Click here.
Now mount.
Yeah, mouse. Okay, it will add automatically.
Now
No. Click here.
click here.
Yeah, click here. Connect. Scroll down. Scroll down. Continue.
Select all. Select all. Perfect.
And continue. Should work now. Wait.
And then for the unzip, for me, it didn't find a data set like this. What I did was specify like the full folder. So like just copy this one and add the /dataset.zip at the end.
Okay.
So that one
Right
just
here.
worked for me.
Nice.
Interesting.
Boom.
So wait.
No, it's in here. It's in here. the
Oh,
dictionary.
sorry.
Wait. This one didn't work for you.
Yeah, so
Click
what I
here.
did is add R in here as well.
Dash R.
Yeah,
Okay.
because it says missing missing destination file operated. Oh, so in here you should just specify the folder. You don't need the dataset.zip file specified.
I see. Yes.
Just the GPT. Sorry.
Perfect. Right here.
Yeah, without the slash. Yeah, kind of
Perfect.
should work. Missing content drive, my drive.
My drive. Yeah. GPTuesday.
Do you
I'm
have
missing
space?
this
Do you have space after?
I do. Yeah.
Before
No. You need
before
space. You need to add space.
Oh, there's no space here. Oh
Yeah.
my gosh, there's no space here.
Yeah.
Yes, you're right. There we go. Now it's like this happens.
It looks
Really good.
Okay, but it's then
Drive there.
GPT. You have GPT here,
Yep.
and you have dataset. So you have to put content GPT and add GPT. Not here. It's already mounted.
Right.
After content, put GPT.
Yeah, perfect.
Yeah. Wait.
Wait, drive, then.
No, you don't.
Yeah, I mean, added that. So content drive, my drive,
Oh,
GPT
okay.
Tuesdays. So
Perfect.
it's content drive, my drive, and then the GPT folder. You didn't specify the folder. Content drive, my drive, GPT.
Perfect. And there we go.
It all ran, and try this one now. should work. Okay.
Okay,
Great.
thank you.
Cool.
So I changed the file path, so it's pointing to this one. I put it here. Do I unzip?
Can you see that
I can send this to
copy of the data set? You just, yeah, you just need to rename this data set to copy of the data set.
Thank you. Okay.
And if it doesn't work, you can try to copy the full path.
Okay.
Let me see.
Copy that.
Rename copy path.
Thanks. Okay, I realized.
Okay. Okay, are we good? Let's move on. So now we will start data set preparation for training. We just remove some garbage that was created automatically. We will read the classes. So you may have to change the past data because you have slightly different path. You can, if you need to know the path, you can click 3 dots here, copy path, and then paste it here. We have 4 classes, and now we will list all the images from our folders, and we will create a data frame, training and test data set. So in our data frame, pandas data frame, we will have 2 columns, image path and the class. And we will use a scikit-learn train test split to split our data set into train and test. We have test size is 20%, and we put random seed usually. If you want to reproduce your results, you always put random state here. So usually when we train the model, we have to optimize hyperparameters like learning rate, some activation function. Like different models will have different hyperparameters, and we have several hyperparameter tuning methods. For example, a random search, a grid search, or Bayesian optimization. The difference is the efficiency. In a random search, after you define space, for example, here's our.
Could we share screen again?
Oh, sorry.
It's okay.
Let's do that.
Yeah, every once in a while, if it sleeps or something, yeah, I might use share screen. Could also be up there, so.
Oh, here.
So just send to the bottom. Perfect. Entire screen. Perfect. All right, thank you.
Mm-hmm. So where we are. For hyperparameters, we define search space for optimization. For example, we will have batch size, hyperparameter, activation function. We will be using different activation functions like sigmoid, TANT, LU, ReLU, ReLU6. We will be using different model architectures like efficient net, inception, ResNet. Those can be used as a backbone. We will be using different optimizers. We will try different number of epochs, and learning rate will be also chosen from distribution, and dimensions in neural network will be also chosen from different numbers. So this is our search space for hyperparameters. If we use a random search, it will be just a randomly selected values from each hyperparameter. Value will be selected randomly. It's not efficient. For grid search, it will try to use all possible combinations of hyperparameters. But for Bayesian optimization, it will run optimization on top of this search space. It's like optimization on top of optimization. We have optimization of neural network parameters, and we have gradient descent for that. And we have optimization of hyperparameters. It's Bayesian optimization algorithm is used here. But it will try to find the best possible combination of your hyperparameters. And here we define neural network architecture. It may look complicated, but it's not. We will have basically our backbone model. Backbone model we call like input encoder. We define efficient net, inception ResNet. These are pre-trained convolutional neural networks that was already pre-trained on huge data set. And we want to use this pre-training model. And on top of it, we will add a pooling layer, which will prepare two-dimensional input for the model, for the output. Do you remember that we had multiple filters on top of backbone model? We add pooling to have a flattened output. And then on top of it, we will add a fully connected layer where we will have latent dimension defines number of neurons in the fully connected layer on top of neural network. And we will have activation function. Activation function will be also chosen from our search space. It could be sigmoid, ReLU, or others. Optimizer will be also selected automatically during optimization. Yeah.
So then how many hidden layers do we have in total? Is it a pooling layer and then the two dense layers? So 3 layers in total for hidden layers?
So on this, here we just define output hidden layers. We will have just one hidden layer. But
Okay.
before that, we have backbone model, and backbone model can have like 56 hidden layers or more.
But this is just the weights of it, right? That we
Yeah, it's just the
inputs.
weights, but we can freeze it or we can unfreeze it. If we unfreeze it, it's not just weights. It will be also backpropagated.
Okay. And then latent dim, did we specify it somewhere before?
In search space, in hyperparameter search space, we define latent.
What does it do again?
What?
What does it do again? Latent dim?
Latent dimension, it's a number of neurons in a hidden layer, in a dense layer.
So is it like a, do we have a specified value for it? Is it 20 and 100 or?
It's here, let me find it. So in this slide, we have, after flattened layer, we have fully connected layer.
Yeah.
And in this fully connected layer, in the picture, you have 2 hidden layers.
Yeah.
First layer is called input, then we have 2 hidden layers, and then we have output layer. And in our example, we just have 1 hidden layer. And each hidden layer has neurons. These blue dots, it's neurons. And latent dim means number of these blue dots in the hidden layer.
So we specified the number of neurons between 20 to 100, right? Because it says list.
Yes, it will be randomly selected.
So it will check each one.
It will check, like not all of them,
Yeah.
but it will optimize which value, in which direction should we increase it or decrease it to find the best.
Using Bayesian.
Using Bayesian
Okay.
optimization.
Okay.
Yes. Next step, we define cross-validation. Wait, here we didn't finish. So after we got our model, we have to define optimizers. Optimizers, it's algorithms of gradient descent. We have different modifications of gradient descent, like stochastic gradient descent or gradient descent with momentum and others. These are just more efficient versions of gradient descent. And gradient descent, it's I think the core power of neural networks. This is how actually it's being trained. Without gradient descent, all of these architectures would mean nothing. This is, I think, the most important part is of AI. And we also, yeah.
The gradient descent helps figure out the activation function.
Sorry?
Does the gradient descent help to figure out the activation function? Which activation function?
No, no. It will optimize weights in the neural network. So you remember you have hidden layers, and in hidden layers you have some random weights. Those random weights will become not random. They will become some meaningful numbers that will help you to find the right predictions.
And is this in a forward propagation?
It's a back propagation.
Oh, and when is the activation function applied?
Activation function applies on top of each layer. So, for example, in a fully connected layer, we have neurons here. And neurons, it's let me find the formula. It's a linear combination. Fully connected layer. Okay, so basically we have each purple neuron here. It's a multiplication of input and weights. Input is our pixels, image pixels. For example, so here, you remember that we saw here this kernel. Kernel is our weight. We multiply kernel with input pixels values. And then on top of it, you see here 53, green color. We apply activation function on top of it.
Okay.
So the 53 will be input for activation function.
Weights times input plus a bias, no? Or something like that? No.
So we multiply inputs and weights.
Yeah.
Then we sum it. Then we apply activation function.
Okay.
By apply, I means we have a formula for each activation function. We have formula, and we have x in the formula, and x value will be 53, and this formula will calculate some number between 0 and 1, like 0.16. This will be result of activation function.
So if you could come back to the code we had, I have a question about all of those if statements. Is it that we will try each optimization function, optimizing, what is it called? OPT, is it optimization, just optimizer?
Optimizer, yeah.
Optimizer, right. So we will try each optimizer function, but what this if statements mean is that we specify that for, because I guess in the previous code cell, when we said Adam, the model doesn't know what Adam means. So what we say in this if statement is we say that if we pick Adam, it has to choose this keras.optimizer.Adam function. And then at the bottom, we say optimizer equals OPT. Will it mean that we will try each optimizer for this to build this model?
We will, during hyperparameter tuning, we will train model multiple times, like 10 times or 50
Okay.
times or 100 times. And each time model will be training using different optimizers.
And then which one, how do we know which one we will pick?
Bayesian optimization will try different optimizers, and the one that which will be the best will be selected. So it will more likely to choose Adam. For example, it will try SGD, it will try Adagrad, it will try Adam, and then it will see that Adam has a best performance. It will increase probability to choose Adam, and next time more and more likely Adam will be chosen.
I see. So as I understand, Adam is a better version of stochastic gradient descent,
Yes.
right?
Yes.
As I learned it, I think it's Adam skips through some steps that SGD would go through. So SGD is like sequential; it would go through all the steps to minimize the loss function, and then Adam, if it sees that like the loss function is constantly decreasing in that way, it would just skip those steps and like make the SGD faster, right, Adam?
I don't remember the exact difference, but as I remember, in momentum, it will add multipliers to the steps
Yeah.
if the direction is right.
Yeah.
But in Adam, it will, I think, calculate a second derivative. So it will increase speed if we going to right direction as well.
Yeah. So it's like liquid, right? So it changes the speed with
Yeah.
with which it
It's more
finds
efficient.
this.
Yeah,
Okay.
it's more efficient.
Can I ask a quick question?
Yep.
Are at this stage in AI and machine learning, are we concerned about compute? Like, are people trying to save on energy when it comes to like worried about using HPC, high performance computing GPUs instead of CPUs, or is like the advantage of using GPUs like just way more advantageous to like the whole use case of AI?
I didn't get the question. So you're asking like, do we have any energy issues?
Yeah, do we have any energy issues with using all GPUs for computing inference?
It depends on the countries. Some countries has energy issues, some countries doesn't. But huge data sensors requires a nuclear powered energy. Yeah.
We're still using CPUs.
GPUs? No. Data.
We're still worried about saving energy using CPUs instead of using GPUs.
It depends on the task. For some tasks you cannot use CPU. It will just take forever to, yeah. So here's an example. You can see that how different optimizers works. So we have a search space. This space is our loss function. For example, a different set of parameters will result in different position in this search space. And if we optimize model, Gradient descent will try to minimize error, and it will find a global minimum in the search space. And you can see that Adam, or one of the best one here, it will just increase speed in some point. And some of them will stuck in local minimums.
Just small off topic. I'm just looking at the paper. I think last month Apple proposed another optimizer algorithm. It's called Ademamics. The names are very weird, but it's like basically like the fastest one on the market. So the field is progressing with every day.
Yeah, that's very cool. That so you basically in neural network you have few building blocks, like you have neuron. Neuron is just simple linear combination. You have activation function. You have loss function. You have optimizer, and yeah, backpropagation algorithm. And you can ask, for example, ChatGPT to improve each of them. I tried to just ask, like, okay, what properties of loss function you can define? And ChatGPT defines you like 15 different properties. It should be able to calculate derivative and not be sensitive to noise, like different properties. And you can ask, propose the best loss function that will eliminate all of those, where all properties will be the best. And it will propose loss function for you. Then you ask, can you try to find possible issues of this loss function and propose the best version of the loss function? It will propose improved version. And same, you can do this activation function. It will create a new activation function for you. Or it can create another version of a neuron implementation, or some improvement of optimization algorithm. Yeah, but with human help, you can keep improving the architecture now. And finally, after we define optimizers, we select how the which loss function will be used. Like cross entropy will be used for multi-class classification. We have, remember, we have 4 classes. 4 classes we use cross entropy, categorical cross entropy. And we will use different metrics. Metrics is just measurement how good the model. We have accuracy, precision, recall, area under the curve. And here we define cross-validation. Cross-validation is a technique to prevent overfitting. If you just split your data set into train and validation and train the model to get the best accuracy in your test data set, it can be still overfitted because your test data set is not representative enough. Then you will reduce probability of the model to be overfitted if you have 5 or 10 test data sets. And then you calculate average value for your test score in each of them. Then it will be a more generalized model. Because if you just have one test data set, model will not be general enough. It will be good enough in one data set, test data set, but it will not be good enough in general.
So if we have one training data set, it's better to split it up into randomly 10, let's say, and run it like that?
Sometimes it's not possible if you have like 2 big data sets and training cycle takes like 2 months. You will not be able to do that. But sometimes it's necessary if you have enough computation power. But basically, if you have like one data set, you split it 5 times, I think you will be using like, but you will still be using like 80% of the data, right? And you will have to train 5 times or 10 times, and sometimes you don't have that time. For example, GPT-5 is being trained like how much? Like 8 or 9 months, and how will you will have to run it 5 times. It's impossible. But if you have just regular business use cases, you have to do this because data sets usually not that big, like million samples, and you will finish training in 2 hours. And spend 10 hours instead of 2, it's not that big issue.
So if you have a smaller data set that makes
Yeah.
that split it up to
Yeah.
to reduce the chance of
Yeah. Otherwise, you will see good scores in your test set, but you put it in production, you will see much worse performance because it was overfitted in your particular test data set. And here we define k-fold cross-validation. We define number of folds, like we can have 5 splits. This is num-folds. Then we read our data set into NumPy array X. Then we get training and test index from our k-fold cross-validation. Then we get our data set, and we run generator. Generator will generate training samples from our data frame. In our data frame, we have paths to the images, label column, color mode, batch size. So this is this part prepares data set to the input, to the neural network. We prepared training validation. In each fold, we still use training and validation. And yeah, we use training and validation. And we run just model fit. Model fit will run model training. We put a generator here. We will put number of epochs, how many epochs we will train. Or we put number of steps. And we put validation data set generator.
Oh, maybe you can go a little bit into the number of steps for the audience, because we see that a lot in, for example, replicate.com, if you're trying to generate images. Could you explain the number of steps for the audience?
Number of steps is usually it's used when we have distributed training. For example, how many steps the model should. So in our data set, we have like batch size. Let's say we have our data set is 6,400 samples, and batch size is 64. And we will have 100 steps. 100 times we have to get new batch and pass it to the model. How many steps we should run to finish one epoch? How many steps we should pass each batch? And in the hist, we will get metrics. All the metrics that we defined here, categorical accuracy, precision, recall, AUC, will be stored in the hist variable and will be printed.
Should it be printed under this cell or?
It's a function. Here it's function.
Oh,
Yeah. And then we define the final block, it's objective, for Bayesian optimization. We put together, so in Bayesian optimization, it will get parameters from our search space. From our search space, it will sample some parameters. And those parameters will be stored into config. For example, in the first step, it will select randomly. Batch size will be 32. Activation function will be sigmoid, model will be efficient net, optimizer will be Adam, number of epochs will be 10, learning rate will be 0.01, latent dimension will be 64. Some random values will be selected from search space and it will be stored in config. Then from config we check if it's ResNet, then we import backbone as a ResNet. If it's efficient net was selected, then we import efficient net. If it was inception selected, we import inception. Then we create generator. We create a backbone object. We build our model. We pass config, backbone, and this, you remember we defined the build function here. It will get config, backbone, and it will create neural network, an optimizer, and it will compile it, and it will return model ready to training, ready for training. Then we create cross-validation with number of folds, with our generator, model, batch size, number of epochs, and when we calculate mean, we will get mean value across 5 folds. For example, we have 5 different splits, our training and test data set. We will calculate mean, and mean value will be used for hyperparameters tuning. And we return loss. Oh, in our objective, we have to define what will be optimized. In Bayesian optimization, we'll optimize mean cross-validation score. From cross-validation, in cross-validation we define validation categorical accuracy. And this value will be optimized by Bayesian optimization. Okay, we defined it. Then we run Bayesian optimization. We create trials. We call fmean. We put our objective function, optimization space, optimization algorithm, number of trials. For example, you can put, if you put one value, just one time model will be trained. If you put 10, then Bayesian optimization will run training 10 times. If you put 1,000, Bayesian optimization will run model 1,000 times, and it will find the best combination of hyperparameters. Oh, 1,000, I think it's too big. So let me stop it. I'll put just one here. So just one time, it selected tangent activation function, batch size 69, number of neurons is 45, learning rate, model inception, number of epoch 1, and optimizer other graph. So it's very bad, actually, it was very bad parameters, but model will be trained here.
I have a quick question.
Yeah.
So for the optimizer, it's looking for the things that you defined in your function, right? And what loss function does it use to find these optimal choices?
So it's not based on gradient descent.
I
It
see.
uses Bayesian optimization.
Oh, okay.
In Bayesian optimization, they use probabilistic methods to optimize. In the algorithms, they optimize parameters of the distributions from which the parameters will be selected.
I see.
So there will be some regressors under the hood that will predict parameters of the distributions. And from these distributions, parameters will be selected. For example, Adam optimizer will be selected with higher probability because the parameters were tuned the way that Adam optimizer will be selected in the most cases.
Okay, thank you.
As a result of this Bayesian optimization, the output we will get is the best optimizer, the best number of neurons, and all of those parameters, like it will try all of them 1,000 times. Well, not all of them, some of them, right?
Yeah.
And then while it's trying, it will optimize its own parameters to see in which direction to go for an optimizer, in which direction to go for the number of neurons.
Yes.
And then it will output the best. So in here, the output for us should be what? The accuracy for now?
What do you mean output?
For this cell.
So the best, it will select the best dictionary with best set of parameters for the model.
But in this example, it won't do anything because it's only one iteration, right?
Yes.
Okay. If it was more, then
Yeah.
we would see the
It
best
will try
parameters.
different,
Yeah.
and at some point it will converge and find the best combination of the parameters.
And then afterwards, we can use these parameters to build our model,
Yes.
right? Okay. So this cell will not build the model; it will just show us the
Yes.
best parameters. Okay.
Yes. This is a hyperparameter tuning step. It will build the model inside to help us to find the best parameters, but it's not the final model yet. Unfortunately, I don't have GPU. In CPU, it will take half an hour. I'll not be able probably to show you the final output here. But let's say after optimization completed, we get a best config and we print it. We see that best was sigmoid activation function.
Do you want to show this one? Swap to my computer and show the...
Yeah.
No, leave it, just change it. Let me change it.
How long did it took?
I'm running it too.
Oh, it's running.
3 minutes.
Mind if I send you the screen guard? You have WhatsApp on you?
What's up? Yeah, I have
Okay,
it.
I'll send screen guard to you.
Okay.
So, but here we also had just one trial, but at least this trial was finished.
Hold on a second. He wants to share it on this.
Yeah, so you can go to your WhatsApp.
Yeah.
And then right there, perfect, perfect. Same thing, so we can put whatever name. We'll be right back. Perfect. Perfect. Let me share a screen, and I'll take it from there.
You good there with the share screen?
And we're live. Perfect, we're good. Thank you.
So you can see that how accuracy started from 0.5. At some point it increased to 0.6, 0.7, 0.7. So it finished training.
Let me kill the sound here so that it doesn't. Let's see if that's better now.
Okay. So, and second epoch started. How many epochs we will have? You put one trial for Bayesian, but we have Bayesian will choose some number of epochs.
Yeah. I think at the bottom it said.
So, okay, at the beginning we have number of epochs will be 2. Okay, it's going to be finished in a couple of minutes.
Is this using GPU from the lab?
Yes.
You can get some credits. Sometimes you can get free credits that you can use. I think I had like a few credits for free, but I also, you can put money in, and it's not super expensive.
Okay.
I prefer to save time and.
Okay. Yeah, free GPU is very cheap GPUs, T4, and you cannot actually train the large models using this GPU, and you don't have a lot of credits. So if you try to really work with Google Colab for your commercial projects, you will not be able to do this. It's better to use Amazon or Microsoft or Google, but in cloud.
Does it specify which GPU on there?
T4.
T4?
Yes. T4, it's yeah, it's chip family. It's good for educational purposes, but not for commercial.
So, if I'm understanding correctly, the initial goal, I thought, was to have like 4 classes, right? Good pictures, bad pictures, and a filter.
Yeah.
But your goal with this wasn't necessarily to give an output, but to train the model so that if it's asked to do the job, that it would do the job as efficiently as possible with the best parameters, with having gone through different k-folds, iterations, epochs, and all those items, I guess?
We not reached to the point where we train the model to predict 4 classes.
Okay.
We just find the best hyperparameters for the model.
The parameter that will help us reach the goal of, well, we're picking the actual model that will show us the classes we need.
Okay.
Yeah, it's still in the middle of the process right now.
Okay.
So you can see best params in the latest cell. Activation function ALU, byte size 48, dimension 97, and so on. And these parameters will be selected to train the model to predict 4 classes.
Okay. And then the other question that I had is that you went through, I guess, different, I guess, algorithms or statistics, but you started off using the what was it you called it? It's not the binary, but the multi-class. If you're not certain, like you have a computer vision project, is there a way to have the model run all 3, or it doesn't work that way?
No, unfortunately, you will have to know what task you're solving.
Okay.
Because usually business defines how many classes you have. If you're uncertain, you have to do some data analysis first. You have to find different cases. Okay, let's say you found 15 classes in your data set. Then you set labels. And but model should know how many classes you have.
How would you determine between, let's say, the two because you one said multi-label and multi-class?
Binary classification and multi-class and multi-label.
Right.
Binary, when you know for sure that you have 2 classes, like black and white or cat and dog, you have 2 classes. But between multi-class, multi-label, it depends what are you predicting. If you're predicting like what numbers you see in the image, you cannot see like 2 numbers together in one picture, for example, in your data. Then you have multi-class. But if you have in your data both classes that could possibly be together in one picture, then you choose multi-label.
So like if you were trying to determine, like with that car image that you showed, speed based on image, that would be multi-label, I guess, right? And not multi-class?
If you predict what speed?
Like you showed an image before of cars, right?
Okay.
So like if someone was trying to determine like speed, so for instance like camera or things like that, speed of the vehicle based on.
So it will not be a classification anymore. It will be a regression problem. So if you have to predict infinite value, you cannot have infinite number of classes. It's a numerical value, you will have a regression problem.
Okay. All right. Okay. Thank you.
Okay, we got one question. Okay.
I'm just going to throw in a bad question. just to make it fun. Since you're so like professional with training the models, we use processes to figure out an algorithm, right? What do you think in the future we'll have to figure out once we taking care of trying to figure out algorithms?
Not sure I got the question.
So like, you know how we have parameters here that make an algorithm?
Yeah.
Okay, in life, basically, they say all things are algorithms, right? Processes.
Okay.
With deep learning and how much advance we receive through this artificial intelligence, do you think there's going to be something else on top of figuring out algorithms that we might look forward to in the future?
Maybe you mean AutoML. So this process that we showed, it's kind of AutoML. ML means that we know for sure what model we will use, what optimizer we will use, what parameters we will use. But if we use optimization on top of it, it's already called AutoML. So this one is, I would call it AutoML model.
So like a continuous flywheel of trying to get the best solution.
Yeah, but you have to know the space where you will find optimal values. You have to define space. If you can define space in your life somehow, I don't know.
Yeah. You have to figure out the space.
Yeah. Yeah, optimization space.
So a bottom and a top.
Yes.
Let's continue.
So then we got the best config values here. We use this config. Can you hear me? The mic is not working. It's dead.
We'll be right back.
Now it's working.
Yeah, we'll get you another.
Okay.
In the meantime.
So now we use this best params to train actual model. We will just select what to import, what backbone to choose, what model to build. We create training and test data set. Test data set we need just to evaluate the model. Then we run model training. So now you see we have already 2 epochs. We already know how many epochs to use, and all parameters we know already. So in my example here, before I was able to achieve accuracy 0.95. It's pretty good. It's good sign if it's very bad if you have like too good accuracy, like 1 or 0.99. It's really bad. It means that you overfitted your model. Yeah. Because in reality, we never have this. We have, I don't know, depends on the task, but we never have that good performance. Okay, and after we train the model, we will have to evaluate it. For different tasks, we use different evaluation methods. For example, for classification tasks, we use accuracy, precision, recall, AUC, confusion metrics. So more metrics you have, better. It will just show you a better picture of your model performance. And here we define just some helper functions like in scikit-learn, they already implemented, in classification report, they already implemented precision, recall, F1 score metrics. And confusion metrics is also implemented in scikit-learn. We just define helper functions, and then we run tests here. here bad performance. Yesterday I was trying to run this notebook. I trained just one epoch with not the best parameters, that's why AUC is low. But before it was like when you just wait a couple of hours, or you will get better AUC here, like 0.9 or something, 0.8. And then after you got your performance, you can also get classification report. You will also see precision recall F1 score metrics here. These are my previous results from the good model. I had 0.9 accuracy, F1 score around 0.8 or 0.1 for different classes. And confusion matrix also shows where the model getting confused. Between which classes it cannot differentiate. And then if you want to use this model in production, we create a mapping between model prediction labels and class names. We create this mapping and we run, for example, we have this example picture. So we have people here, we have, I think it's good quality, yeah. So we run model prediction, model predict image preprocess, and we get numpy argmax, means that we select the class with highest probability, and we get the value, and then we use mapping. We use mapping to get the class name. It's good quality photo. This is how classification model can be used. So, do we have model? Yeah, training is finished. Let's see the performance we got here. In my predictions, we have, like we reading our image, we pre-process image, then we run model predict, and we get argmax. And the pre-process image, let's see, different backbones will have different pre-process function. You see that ResNet has its own preprocess input. EfficientNet will have its own preprocessing. Inception will have its own preprocessing. And let's run the evaluation. Okay, looks better now. So we trained pretty good model. Test AUC 0.96, recall 0.77, precision. Precision. Do you have another mic?
No, the turn is the button. Press the button.
Okay, now works. Precision 0.86, category accuracy 0.89. Yeah, it's good. Good enough. We can run test to get classification report. So you can see it takes several minutes on GPU to train on small data set. I think we will like it to get a good enough deeper parameters at the first step. Usually we get a very bad sample, then performance will be poor. But you got good one here. And you don't need to define all possible optimizers here in your search space. I think you can just leave a couple of them that you want to compare. And you want to just leave a couple of activation functions that you want to compare. You don't need to list all possible scenarios to save your time. You just can keep the one that you really want to compare. Okay, so. Taking long. So I think we can finish here. I think we covered everything that we planned. Maybe next time we can go through object detection.
Yeah?
Yeah, today we didn't have enough time for object detection, but next time we can go through it.
Sounds great. Sounds great. Yeah, next time we can do object detection. I'll come on up. Amazing. Thanks. Amazing, amazing. Thank you so much, Aleksey. I think everyone learned so much about object classification and computer vision. Who here learned something new about computer vision today? Oh, look at that. All the hands up. All the hands up. Amazing, amazing. Well, thank you all so much for coming. And this is one thing that we really want to provide. It's just really incredible GPTuesdays workshops so that we can continue upskilling and learning something new from incredible folks in our community. Aleksey Romanov being one of them, just one of our most talented, brilliant engineers here at GPTuesdays. And this is the kind of quality that we want to continue providing. And we want to continue making it better and better every single week. So how about ask a question to the audience. What would you like to see in the future for one of the next GPTuesdays workshops? Anyone? Christian?
Definitely more deep learning, nuts and bolts, metrics, parameters.
Deep learning, nuts and bolts of the different parameters, weighing, and all that kind of stuff.
The metrics, the parameters, the activation sequences, so that we can learn how to get our hands wet and program and training.
Got it, okay. So on more on the programming side, on the deep learning, okay, go ahead.
I guess maybe go a bit more in depth into the math in some of, because we see all of those optimizers, but we don't see the math behind them. It's obviously very complicated, but I think going through some of it and at least going away from the workshop with understanding of some of the math would be nice.
Okay, great. Yeah, so that's something that we haven't explored, but I would love to explore that at some point. Stop going deep into the math so we can find out why this is even working, right?
Maybe they misunderstood it, but
yeah, I mean, Alex Comerford is somebody that would be very great for this. I mean, I know Aleksey is too, so. One more?
We can have Aleksey use ChatGPT to go into the math that he wants to see if that works out.
The Wolfram Alpha plugin with GPT. And yeah, how about anyone else? Any more recommendations for one of the next GPTuesdays workshops and all?
Maybe some basics.
What was that?
Like
More basics? Got it. Understood. Actually, we will be having one more on the basics very soon by Eileen. So stay tuned. That'll be a very fun one. So, essentially have different areas, right? So we can start with intro, we can go deep, we can go into math, we'll cover it all. That's definitely the plan. Anyone else? What else would you like to see? I'm going to put you on the spot, Alex. What would you like to see in the future?
Sorry, two on the spot.
Two on the spot. Yes. I was joking in that regard. Anyone else? Any more? So some other feedback that we've received as well. Some people would like to cover, machine learning operations. ML ops. Maybe that's something.
Maybe more on data preprocessing, so like getting a dirty data set and like going step by step to clean it out.
Fun. Yeah, exactly. I mean, but yeah, that's a very important part of all of machine learning, right? Being able to clean up the data, getting the data in there. And I think that'd be a great way to also experiment and make sure, because that's testable too. So then we can come in with a dirty data set, at the end of it, how accurate are we, right? So we can have that, we can have someone look into it and provide feedback from one of our instructors.
Because on all presentations, the data set is already clean from Kaggle or from anywhere else.
Right.
And then in like when you're on a job, you have a data set and it's terrible, right? So you have to do something with it.
Yeah, you have to do something with it. It's incredibly important for those that don't know, machine learning, data analytics, and data pre-processing is one of the most important steps. So go ahead.
Well, since you already covered quantum, AI, machine learning, the professor, I think, uses machine learning and robotics. So if you do a session on that, and then maybe VR and AR, augmented reality, virtual reality, because those are cousins. So.
Right, yeah.
So we use reinforcement learning for the AWS, training the car, the self-driving car.
Great.
So if you take the machine learning class, when you do the section on reinforcement learning, you will train an algorithm, put it in the car, take it out there and see if it works or it doesn't work. And who goes fastest around the track wins the best grade.
Yeah. So the best test would be speed?
Well, that's the interesting part, because when you do it in theory online, there's no inertia in the curves, so it doesn't spill over. There's no confusing in the computer vision part due to shadows or light. So there's a big difference between training a model in a simulated environment and then taking that model and putting it in a real environment, and you see all the difference between the simulated environment and the real environment, right?
Wow. What simulated environment do you use?
That's the one that's provided in our case by AWS. So if you go into AWS Deep Racer, you can create an account for yourself and you can train a model for yourself. And if you want, one day we can, if there's enough interest, we can have you all train a model. And then one day we set up the track here with the car and you can all see if it worked or not.
Yeah, that sounds very exciting. Who would like to see that? I know I would. Hey, look at that. There's all the hands up. Amazing. Super exciting. There we go. Let's do it. That sounds like a very fun one. And so, yeah, I just want to do a little bit of housekeeping now that we've covered. Were you bringing up something that you wanted to see earlier, or?
I mean, I'm definitely interested in how to run models locally, when you, like, collab is really helpful, that's why I started other ways.
Right, so how to run machine learning models locally, right? And kind of getting set up and et cetera?
Yeah, I guess it would be a little bit like basics.
Right, so on the basic side, yeah, absolutely. So we're actually working with someone right now to get one of those intros for one of our next GPTuesdays workshops. So we're very excited for that. And we'll go ahead and do an email blast and everything, Telegram blast. You know where to find me. You know where to find us. And so, yeah, well, with the final housekeeping, the next few weeks we have some very exciting developments. Right now, GPTuesdays Brazil is actually starting to expand, so that's really, really fun. We have the University of McKinsey that, we have a lot of students in, and we're broadcasting all the stuff in Portuguese, subtitles, etc. So we're reaching out to the students over there as we start spinning up in Q1, Q2. And beyond that, next week we have Tal. He worked over at Cisco and Visa. He was one of the heads over there. And he's going to be talking about the road to AGI, the human march to AGI, kind of, how we've gotten to where we are now, what are the next steps to essentially get there, and some of the ethical and responsible AI considerations that we need to consider. AI governance is going to be incredibly important, so it's one you don't want to miss. And I know that Miami-Dade College is also having OpenAI here on December 10th. So if you want to swing by and learn from the best, it's definitely going to be a great session. And beyond that, December 10th, we also have the quantum computing seminar. We'll be bringing folks from around the world in order to discuss quantum computing technology. Everything is moving so fast, so we want to be ahead of the fourth industrial revolution by educating the local population, bringing governments, academia, and industry professionals so that we can all learn together. I think it's super important. So let's give it one more round of applause for everyone here. And one more round of applause for Aleksey, our great instructor. Yeah! And without further ado, see you next time. Amazing.